Thank you. Well, I would like to thank Harold and then the organizers to invite me to this wonderful place. And I learned a whole lot from this couple of days. So I'm going to talk about our recent results about the electrical switching of antiferromagnetic hematite. In this case, it's the alpha phase iron oxide. And so these are my collaborators who contributed significantly. I mean, these are my students. They did the work. So I don't have to give much introduction about the electro control of the spins, including the antiferromagnetic spins. So I'm going to give a quick introduction about how we grow our films, and then the characterization of the quality of the hematite films, and then our experiments on the electrical switching, and then the control experiment, as well as the Monte Carlo simulation about the switching process. So I'm going to start with this. So the ferromagnets are relatively easy to control. They respond to external magnetic field, such as the magnetic hard drive, but also they respond to spin torque. That's the whole field of the spin transfer torque, starting from the magnetic tunnel junction, and later on in these bilayers that involves either a heavy metal or topological insulator. You can pass a current, and so the accumulated spin will manipulate the ferromagnetic magnetization. Well, on the other hand, as we heard a lot during this workshop, that the antiferromagnets are not as easy to control. They don't typically respond to external magnetic field because they have no net magnetization, but they respond to spin transfer torque because it's a microscopic interaction, and then the torques just work out to you can exert on the antiferromagnetic spins. So there are a lot of exciting works, outstanding work recently, and I'm just give two examples. One is by Professor Youngworth. This is the electrical switching of the metallic antiferromagnet, in this case the cobalt manganese arsenide. And another one is in the bilayer system by Professor Song's group. This is in the antiferromagnetic nickel oxide and platinum bilayers. So we use a technique called off-axis sputtering to grow all kinds of oxides. In this case is the hematite. So we have several chambers, sputtering chambers, and then small chamber for MBE growth of DI. So in one chamber we have really good vacuum, and then the other two are in the 10 to negative 9 scale as well. So I'm going to just give a quick overview why we use off-axis sputtering. What is the difference between that and the conventional sputtering that we're all very familiar with? So conventional sputtering, we call it on-axis, that you have a sputtering target, you fill in argon or a mixture of argon with oxygen, for example, and then you apply a power, either RF, DC, you ignite the plasma. So the energetic bombardment of those ions will eject the atoms. So the conventional sputtering technique, you put your substrate directly facing the target. Okay, that's called on-axis. And then, understandably, you're going to have pretty energetic atoms being ejected. And there are some measurement to measure their energy. It could be from 10 to 10s eV. But if you have oxygen in there, you're probably also going to experience some oxygen bombardment as well. On the other hand, if you put your substrate not directly facing, but at a certain angle, in our case, we put somewhere around 60 degrees from the normal. In that case, not only we avoid the relatively high energy ejected atoms, and then this plasma bombardment, somehow from our experience, the atoms coming out of this angle also has a much lower energy, such that it's going to give something like an MBE growth energy-wise, because just from the quality of the films we use. The downside of this geometry, of course, is your growth rate is going to be significantly lower. So, but compared to PLD or MBE, it is comparable or could be a little faster as well. But since we only work with relatively thin films, from a few to 100 nanometer, so this is not a problem for us. So, well, this is an overly simplified hexagonal structure of the hematite. In reality, the atom may be a little offset a little bit, But in general, you have a ferromagnet aligned. This is the supposed to be the high temperature phase. Ferromagnet aligned plane, but alternating between the planes. So we first grow this on the C-axis, or the 001 oriented sapphire. And we have, this is the substrate 006 peak, and then this is the iron oxide. So if you look closely, the reason, okay, so this is the main iron oxide film. These are the, what we call Laue oscillations. So when you have a homogeneous film, so the thickness also is going to be superimposed on the crystal lattice. So that's why you have these beads. And there's a little background here because this particular sample, we have a 2 nanometer platinum on top. It happened to be the platinum 111, I believe, also is here, but it's not going to interfere with the observation of those Laue oscillations. And then we did the rocking curve of this particular peak. That's the 006 of the iron oxide. And we saw a half width, full width at a half maximum about 0.04 degrees. This is the XR, X-ray reflectivity measurement. So from there you can see confirm the thickness, but also pretty smooth film and sharp interface of the order of 1 angstrom. So this is the STEM, or the scanning transmitting electron microscopy. We have an excellent electron microscopy facility at Ohio State. So this is a cross-section view of hematite alpha phase iron oxide grown on aluminum oxide. This is the 001 oriented. You can see that the lattice continuation, so it's the same hexagonal lattice. You might notice that we have a little blurb right here. This coincides with this 5% or so lattice mismatch between the iron oxide and the aluminum oxide. So by definition, they need to relax. So the 5% translates to a 1 defect every 20 lattice constants. So that's roughly what we observe. But above this first couple nanometers, the atomic arrangement seems perfect, well, within this view. And that is the top surface. Okay, so this is the iron oxide. Here's the platinum. It turned out, our electron microscopy collaborator told us, the platinum, the FCC lattice of platinum, and this hexagonal lattice of iron oxide along the 001 direction, the lattice mismatch is only 0.1%. So you can grow really high quality epitaxial film on that. Right? Imagine the 101 platinum, which is its favored orientation, grown on the 001 axis of the hexagonal lattice. But we grow this at room temperature, but within this view, it appears epitaxial. All right, so this is the AFM, this is still the characterization. This is the terraces from the surface. This is 30 nanometer hematite. And this is the platinum on top. They all kind of comparable, 0.1, 0.2 nanometer, so give a pretty smooth growth. So, and then we check the magnetization. Okay, so in the high temperature phase, okay, so the film is in the high temperature phase. It is antiferromagnet, but with a very small kink. Okay, so that is turned out to be about 2 EMU per cubic centimeter. So first, when we measure this, it appeared to be nothing. But recently, we measured 100 nanometer, and we did see a little hysteresis, and that corresponds to about the bulk value. So there is a kink that can give you a very weak ferromagnetism. So that's an update to this. All right, so now let's look at the 0001 surface of this hexagonal lattice. So it's obviously a hexagon. Okay, in this case, you have the iron atoms at the corners. And then from the previous literature, it turned out it stay in plane. Okay, so it really doesn't want it to stay out of plane. But within this easy plane anisotropy, there is a weak, we call it triaxial anisotropy. So it turned out to be along these 3 directions. Okay, this double arrow direction is where the antiferromagnetic spins like to align. Okay, and that actually agree with what we observe from our measurement. So we use, we have a MB chamber, so we have a reed, so my student use reed to align the crystal orientation and then make this pattern. This is an optical picture under an optical microscope, and that is a scale bar of 10 micron. So I told them to use X-ray, which can also align this, but they like to use reed, but either way it works. So we pattern this into an 8-leg structure. This is a little different from some of the other groups used because they are basically symmetrical 8 legs. Okay. This, we have these 3 legs that are thick, wide legs that are 60 degrees apart instead of 45. This is just to coincide with this 60-degree rotation between the 3 easy axes. And then in addition, we patterned the 2 smaller, narrower lines as a voltage detection line. All those 3 main lines, they are 10 micron wide, and this is 5 micron. So the idea is, along these 3 thicker lines, we're going to send current, the pulse current, to try to switch the antiferromagnetic spins. And then after that, we're going to send a sensing current along this leg, which we labeled as E2, and then detect the voltage along these 2 voltage legs using something like this Hall geometry, typically, as we have seen from the talks today. All right. So that is what we got as a pattern. And then we hook up the wires into these all 8 wires. So we start from a fresh sample. We send a chain of pulses. In this plot, each chain is 10 pulses. And we use a 9 milliamp current, pulse current, and the width, initially we use 5 milliseconds, and then later on I told them to change to 1 millisecond, and there's no difference in the result. So we stay at 1 millisecond, that's kind of limited by our Heasley instrument. We are trying to buy some nanosecond pulsars. But anyway, this experiment I presented today, they all on 1 millisecond pulses. 9 milliseconds correspond to 4.5 times 10 to the 7th amp per centimeter squared, or 10 to the 11th amp per meter squared. So that is the scale of the pulse current. So we send a current, each dot corresponds to 1 pulse, and then after each pulse, we wait it for 30 seconds, make sure it's kind of the temperature or whatever things can come back to the equilibrium. And then we send a smaller current. The sensing current we use is like 0.3 milliamp or so, very small compared to the pulse current. It's a DC, and then we measure the voltage. And that is what we plot here as delta R xy. So for the initial chain along E2, this is horizontal one, they are more or less staying at a constant. And then we change the current, pulse currents along the E3, 60 degrees apart, away. And then the voltage, suddenly the detected Hall resistivity jumped to a higher value in this case. Okay. For 10 pulses, they stay more or less flat. And then we change it back to E2. And it dropped back to more or less the original value. And then for 10 pulses. And then we change it to E1 along this direction. And it's going this way. And then this is repeatable for however long my students were patient to measure. All right. About several hundreds of them, pulses. Okay, so now I'm borrowing the equation that Professor Song showed actually come from an earlier paper. So the spin torque acting on an antiferromagnet has the net effect of aligning the spins, antiferromagnetic spins, with the pulse current. And that is given by this equation, this is the precession term along the anisotropy axis, and damping, and this is the spin torque term. And then spin polarization is here, L is the Néel vector. All right, and then spin Hall angle, current, etc. So the net effect is to align the Néel order, the antiferromagnetic spins, with the pulse current direction. Okay, so then what is the mechanism of detection? What we tend to believe, is this is something like the spin Hall MR but in the Hall geometry or transverse geometry. So it's kind of spin Hall, anomalous Hall effect. So let me continue on. So this is purely electrical current manipulation and electrical detection of what we believe that reflect the spin configuration in the hematite film. To kind of confirm what we believe it is, so we did a field scan. So this field, we applied it in plane, in the plane of the hexagon. So we rotate this about 360 degrees. So iron oxide has a pretty strong out plane as such. Well, you want to say in plane, but within the plane, it doesn't take a large field to induce this spin flop transition. Spin flop transition is when you apply a large enough field, the antiferromagnetic spin like to align perpendicular to the field to minimize the energy. So that's what we observe. So somehow this 1 Tesla symbol is not showing, I don't know, the color. Okay, so basically, if you look at the 3 Tesla, it's a nice sine wave. So along 0 degree, 0 degree is parallel to the E2, and then you rotate. It has this orientation because what we're measuring still is along these 2 voltage lines. So when you do the 3 Tesla along this direction, the spin orientation is going to be vertical, up and down. And then when you rotate it to the field this direction, it's going to be horizontal. So it follows your field direction, but in the perpendicular way. So and then as the spin rotates, your voltage detection is going to be following this sine theta angular dependence. This 1 Tesla, just trust me, is basically directly overlap on this. So 1 Tesla is enough to induce the in-plane spin flop transition. However, 0.1 Tesla, you can see this is really not a nice sine wave, a sine angular dependence. It's just we believe it's below the in-plane spin flop transition. Okay, so I'm going to come back to this a little later. So here I just labeled the different places where the angle is along the 3 axes where we patterned the sample. So now let's see the current dependence, pulse current dependence. So right now I'm going to use only 2 directions. I believe the E3 and the E1, just these 2 directions. So the previous plot I showed is 9 milliamp. So that corresponds to 4.5 times 10 to the 7 amp per centimeter squared. And then we go to 10 milliamp. Okay, you can still see this square wave like switching. And then 12, still square. Starting at 14, we see in addition to this square, there's a slope. Okay, you continue to increase that until 16, you see this much larger magnitude. We call it either sawtooth or triangular wave. It is qualitatively different from what we saw at a lower pulse current. So what's going on right here? So to find out what is causing this change, we apply an in-plane field. So we apply an in-plane field. The idea is that if we apply field high enough, like 3 Tesla, we should be able to lock the antiferromagnetic spin along certain direction. And then, like we expected, at a 10 and 12 milliamp, when they show more or less square waves, you become flat. That means the field of 3 Tesla is enough to freeze it. No matter which direction you pulse your current, it's not going to respond. So you always measure the same spin configuration in this situation. But at the 14 milliamp, we see that it changed to something like the triangular wave or the sawtooth, while this little plateau thing kind of gone. And then at 16 milliamp, it is essentially unchanged. So we plot this pulse current dependence of the Hall resistivity we measured. Let's say this plot, just measuring the delta right here. We plot here, remember, this is the log scale, this is linear. It is really not a linear or exponential dependence. So we cannot call it whichever way that is. So this one, however, after you freeze it with a 3 Tesla in-plane field, the magnitude of this, well, this is although a flat line, when you zoom in, there's still tiny magnitude. It is exponential, so the semi-log plot. So we'll come back to that later. So now I'm going to replot the previous two and group them differently. For the 16 milliamp, which is the highest in the previous plot, we show here is the 0 Tesla, which is the blue, and then the 3 Tesla, that is the red. They are more or less the same. So they have a very large magnitude. They show this triangular wave, and then it decay or it reduces in magnitude, as we have heard a couple really nice work earlier today. So for the 12 milliamp, which is the square wave section, so the blue one is zero field, so you have this pretty nice square wave. And then for the 3 Tesla, it's more or less flat. But if you look closely, there's a little bit zigzag going on right there, but more or less flat. So these are clearly two different regimes. Okay, so we're going to find out. Let's do some more experiment to try to find out what's going on. So we notice that the 16 milliamp compared to 14 or 12, the magnitude increased a whole lot. So we suspect there might be some heating effect or annealing effect going on. So we went even higher, not too high to burn it, but 18 milliamp, which is quite large. So we tried the 18 milliamp, and I think my student also did this measurement. They saw this kind of sawtooth, but with a quicker decay. And then come after the 18 milliamp and come back to the 16 milliamp. So we call this blue one a fresh sample that hasn't seen the annealing at 18 milliamp yet, but this red one is 18 milliamp, after 18 milliamp annealing. And it shows a pretty flat square wave behavior. And then we apply a 3 Tesla field for the same measurement. The blue one, the fresh one, you have seen that before, remain essentially unchanged, but this red one become flat. That means after the 18 milliamp, we call it annealing, that zigzag feature, the triangular wave feature is gone, and the field can actually freeze it, just like the previous 12 milliamp. So now the new 16 milliamp behaves more or less the old 12 and 10 milliamp, the low current regime. So somehow this annealing largely got rid of this, whatever caused this triangular behavior. Okay. So we apply high current annealing. Even for the 12 milliamp, the blue is before the annealing. Although it's pretty square, but you can see this a little change during the plateau. But after the annealing at 18 milliamp, it becomes much more square. And this actually we can repeat for hundreds of without seeing any decay in the signal. And then you apply 18 milliamp, apply 3 Tesla, and both the fresh and the after annealing one become more or less flat. So now let's see. So we anneal it, and then we vary the pulse current magnitude from pretty small, 6 milliamp, to 16 milliamp. And they all show square wave feature, but the magnitude are different. Okay, so clearly larger at 16, and then getting smaller, and then still detectable at 6. So we plot this magnitude of delta R as a function of the pulse current magnitude. We notice that except this 6 milliamp one, the others fall on this linear dependence in this linear plot. Both x and y are linear. So this is a linear dependence. So what can cause this linear dependence? So here is a relatively hand-waving explanation. After annealing, let's say if you can switch the antiferromagnet, it should come from the spin transfer torque. And that torque should depend on how much spins you accumulate at the interface. And that number of spins should be linearly proportional to the pulse current magnitude. We apply 1 millisecond, so it's very long. So let's not consider the time effect. But this is directly proportional to the pulse current on the magnitude. 6 milliamp is away from there, so there must be some nonlinear dependence when you have a low pulse current. All right, so now I'm showing this temperature dependence. This is the temperature dependence at 9 milliamp from 300 Kelvin down to 200 Kelvin. So the 300 Kelvin, pretty square and then square. As you go down, the magnitude decreases and it's essentially gone at 200 Kelvin. So, and if you plot the delta IXY as a function of temperature in this semi-log plot, it shows this exponential decay. That means this is a thermally activated process. So whatever a certain amount of current you put in there, it needs certain thermal energy to make the antiferromagnetic spins to go over the barrier, let's say called hard axis, to go to the next easy axis. So that is clearly a thermally activated process. And it's going to freeze out at a lower temperature. The antiferromagnetic spins are frozen. So at this current, we're not able to switch it. So now come back to this high current behavior, 16 milliamp. This one, since we pass a higher current of 18 milliamp, it kind of get rid of it. So we were wondering what could cause this. So we deposited a 2 nanometer platinum directly on the substrate of sapphire. And then at zero field, it shows basically the same behavior. And then when we go down the current from 16 to 14 to 12, this triangular wave form more or less persists, just smaller in magnitude. And then when you plot this dependence of the delta Rxy as a function of the current, it is exponential. Somehow it's kind of like thermally activated. Now we pulse 18 milliamp of this control sample, and then the magnitude reduced by a lot, although it's not totally gone. I mean, although if we go to higher current, we probably can further reduce it. But as we heard from earlier talk, this could be some annealing or heating effect that we think we are driving the green boundaries or make it grow or somehow, and then a higher current kind of reduce the number of green boundaries. So that's another current dependence. So right here, so this is the control sample, and this is the iron oxide, and then here is the 3 Tesla. Okay, as a comparison, I just labeled them here. And then this is the dependence of the delta Rxy as a function of the pulse current. You can see this is linear, this is exponential, and that is exponential, and this is together, they are pretty undefined. So let me see what I have here. Okay, so here, yes. Now let's talk about the magnitude. This magnitude at the highest current we apply 16 milliamp. Sorry, at 60 milliamp, it's about 0.02 ohm in the delta Rxy. If we bring back the field control, we apply 3 Tesla in-plane field. And if you look at the top and the bottom, that is 0.27 ohm. So the field is, I think it's a cleanest experiment. You lock the spins to rotate very clean. Well, the pulse current, you switch something, you're probably not going to switch everything. So what is the difference? This is a factor of 13 different. So now my student did a Monte Carlo simulation by applying, this is the effective field of the, okay, so this is the exchange interaction, this is the in-plane anisotropy, and this is the spin torque driven effective field given by this. You pay attention, it's proportional to the current. So by plugging this into the simulation, you can say if we ramp up the H effective, which is the same thing as we increase the current, and then you follow this, we call it the initial curve, you can saturate this. But then our measurement is done after we remove all the pulse current. So you need to come back. And then it's going to be much lower than the saturation one. If you ramp up to middle, not saturated, come back, is come to a lower one. So the comparison, so here, we also did a field, this is experimental data. So we apply a field, in-plane field, perpendicular to E3 along this direction. We ramp up to 1 Tesla, which is enough to saturate it, and we measure the RXY along the way. And then we lower the field. You can see the RXY is going this way. That means after you reduce the field or you eventually remove it, it breaks into multiple domains. Okay, that's what we believe is happening. Exactly why it happens, so that I don't have a solid answer. But if you ramp up to like 0.1 Tesla come back, the value is going to be smaller, kind of like this Monte Carlo simulation. Okay, so here is my summary. So I'm not going to read it, but like other people have said, I have 2 postdoc openings in my group. So if you're interested, please. Yeah, thank you.
What about this effective field? I think there's normal field. It's simply the Earthly field we generate because we have the high conduction platinum layer.
The Auster field. Yeah. But the antiferromagnet is not supposed to respond to a
free pressure.
So okay, we haven't calculated how much the Auster field is. We apply, 9 to 16 milliamp. Yeah, so it's, yeah.
So it's just on top of it,
right?
And this reacts to fields of the order of, I don't know, I mean, the free Tesla seems to saturate the whole thing. It totally strip flux the whole thing. So I could imagine that the Ørsted field has a similar effect. From the symmetry, it's actually the same. Like it could also, it's the spin flux mechanism, how the field, external field acts on it.
Although it should be, perpendicular, the field should be perpendicular.
Yeah, so it should align the electromagnetic part.
So we will calculate. Yeah, we haven't thought about that.
Yeah. It's probably like 10 billion Tesla.
That's what you estimate? Okay.
So 2 questions. First one is you said for the 30 nanometer film, you did not see any magnetic moment. However, we would expect that.
Actually, I should take back. So my student did a more careful. We did a screed measurement because the large slope. There seems like a loop in the middle, but on the high field, it's kind of pretty weird kind of shape. So there should be something in there, although we were not sure. But so we grew a thicker one, and that's also cleaner moment. That's agree with both.
And the second question I have is the thickness depends on the switching. I think something we didn't discuss so far.
Iron oxide, you mean?
Yeah. In general, I mean, 30 nanometer is quite a thick film. So if you calculate the efficiency, it would have to be rather gigantic.
So here's the interesting thing that we didn't put in the paper or I didn't talk about. This thing has a pretty weak thickness dependence. So we did something like 20 nanometer, 50 nanometer, 60 nanometer. The amount of current needed is more or less the same, considering the sample fluctuation.
So do you think it's because you're not switching the whole thickness, but switching only the top layer?
I think you're switching the whole thickness, but in the antiferromagnet, it's very different from in ferromagnet, you have to overcome the big magnetostatic energy. In antiferromagnet, it should depend on the thickness, but it's not clear that it should be linear or inversely linear. But yeah, that's a great question. We were thinking about it. There's a very weak thickness dependence.
So maybe I can comment on that. This is exactly the same what we also see in our platinum manganese nitride experiment, and it's related to the grain size distribution that you have. So this is what I've shown, that you always switch the same delta depending on the temperature, and that means that you basically select with the spin-orbit torque strength that you have available different grains. And then when you have a thicker film, you just switch narrower grains. So the volume is still constant. This is kind of.
So you saw similar in the manganese nitride?
Yeah.
And first I would like to ask one question. Why for your detection signal spin core anomalous core detect?
Yeah.
Does SMR should be also okay?
You mean to call it?
Yes.
No, I'm not attached to that in labeling. I'm just saying it's related to the spin Hall MR, but in the transverse geometry. So, I mean, anomalous is reserved. I know, it's a terminology, I agree. Whatever you call it, this is due to the spin-torque interaction at the interface, somehow reflecting in the transverse direction, just similar to the SMR along the longitudinal direction.
I also want to add 2 comments on combining your results. The first, I think the switching features are dependent on the system, on the materials. This one step or sawtooth switching features especially depends on the anisotropy. As I showed in my experiments, for example, for magnet gold, switching from the hot axis to the easy axis is one step. But for the easy axis to hot axis is difficult for sawtooth. And so this is especially depends on the anisotropy. For example, when I switch to YID, this biaxial YID, this is also one step switching. Because of the anisotropy of this iron oxide is quite small. So the switching is one step.
At least from one easy to another easy, I believe.
Yes.
Yeah.
The second comment is just my comment. Okay. It somehow we call it thermal effects or migration or annealing. Anyway, the cycling effect, the cycling property for this kind of artifacts is worse than the real magnetic structure switching.
Worse, you mean?
Yes. You could see, for example, for Peter Modern science paper, you could see the switching signals. It's so beautiful. 1 point by 1 point, the switching is perfect.
Yeah.
Each time the signal is the same. For your signal for these artifacts, you could see the cycling. The bigger, smaller, somehow is not so consistent for each.
You mean the, let's say, for example, the platinum on sapphire directly?
Because of the annealing and the...
Yeah, it has a history. Yeah, it's going to decay.
The migration is not so repeated.
That's right. It's not
So when we do our experiments, we could detect somehow from the cycling property how much of the contribution from the artifacts. Especially in your experiment, it is 0 and measured under 0 Tesla, I mean without magnetic field, and 3 Tesla, there's also some difference. This might also the contribution from the magnetic structures.
I agree. So when we apply a 3 Tesla, we kind of freeze out the magnetic switching part. What's left should be whatever happened in the platinum. Okay. Kind of, I mean, we saw a little, I mean, it's a smaller magnitude, but it's there. Yeah, okay. I agree. Yeah. Yeah.
Maybe just a quick comment about the spin hole magnetic resistance.
Yes.
That's symmetry-wise the same symmetry as AMR.
Yes.
We also showed it was even in the magnetic moment. So basically in AMR you have the longitudinal and transfer signal.
Yeah.
And that's why you also have in SMR longitudinal and transfer signal. It's just SMR. It's just
Yeah.
Question. When you see the decay, when you go with the magnetic field back to 0, so it looks like you're not switching it permanently.
So which data you're referring to?
It was one of, yes, here. So you go up with the field, and when you go back.
This one.
Yeah, when you go back, it actually relaxes part. Right?
That's right, yes.
So it looks like, so my question is, did you do this experiment for aligning field along also E1 and E2 axes? Because it looks like they are not equivalent. Maybe because of the macrostructure, you're not making the 3 easy axes.
Okay, E1 and E3 are same in magnitude, opposite in sign. And E2 is different. I don't think my student did other directions. But okay.
My suspicion is basically the 3 axes are not equivalent, and then the system tends to relax with the easiest of the 3 maybe, and that's why you can have the relaxation.
Well, in my view, these 3 are equivalent if they have like close to ideal system. But the measurement, because symmetry, E1 and E3 should give same magnitude but opposite in sign signal, while E2 will give a different signal.
No, but it relaxes. You don't orient your moments permanently.
Right. So it's going to break into multiple domains when your field is lower.
Right. Why?
That's the question. I don't know. Like it's like ferromagnet will break into multiple domains. Yeah. So that we don't know. Yeah.
Last question. Did you look at relaxation of the electrically switched domains?
Relaxation meaning just wait.
Without pulsing.
We have done, I think my students have done like 500 pulses, and they stay basically the same. Not perfectly the same, but kind of like it stay in a plateau, like the first one we show, like something like this. This is going to stay like a plateau for 500 pulses.
Without pausing, so you just measure the...
Yeah, just we pulse a number of like, I don't know, 1 or 10, and then just keep measuring after every 30 seconds. It's going to stay. Yeah, that's stable.
All right, so that brings us to the end of the day.